Okay, so for this problem, we have a schematic eye, and we put a +5 sphere in front of the eye. So when it comes to these kinds of problems with schematic eyes, whatever lens we put in front of the schematic eye, the refractive error of that is the exact opposite. Okay, so in this case, the refractive error of the schematic eye would be -5. Okay, the reason for that is when we say an emmetropic eye, we say that it has hypothetically 60 diopters of power. So this schematic eye has 60 diopters of power. If we put +5 diopters in front of it, we end up with 65 diopters. What that means is to neutralize that and to return them to emmetropia, we'd have to neutralize that refractive error with -5 lenses. Back to 60. Okay, so the reason why that makes sense is that we know that myopes have more power than normal and hyperopes have less power than normal, which is why we correct myopes with minus lenses and hyperopes with plus lenses, because hyperopes need additional power to reach emmetropia. So we know that the refractive error for this patient is -5. At what distance would you see neutral? So I'm just going to remind you that in terms of retinoscopy, you cannot neutralize any plus power with just distance. You need to add lenses. When it's minus powers, you can correct that with distance. The reason for that is that depending on what working distance you choose, after you're done with retinoscopy, you subtract that out of the phoropter, right? So if you are working at 50 centimeters, you know whenever you hit neutral, you then take your working distance out, which is -2 lenses added to whatever's in the phoropter. So on the off chance you had a patient whose refractive error was -2 and you are working at 50 centimeters, you would see neutral with the phoropter at 0, you'd take out your working distance, and you'd end up at -2. So in this case, the refractive error is -5. The easiest way to find out the distance is just to find the punctum remotum. So you do 100 divided by 5, and that's 20 centimeters. Okay, now for this next part, we have at what distance would you see 1 diopter of against motion? So 1 diopter of against is the same thing as 1 diopter of minus. Okay, so we know these two formulas, gross equals working distance plus net, or this is the way I think of it, which is like backwards. So theoretically, when it comes to working distance, it's plus power. But since we end up taking it out, like we end up putting minus into the phoropter, I've always thought of it as gross plus working distance equals net. When you flip the formula in this way, so instead of making gross equals working distance plus net, if we switch that to gross plus working distance equals net, then you can just use the sign of whatever you're taking out. So what I mean by that is, if we use the usual formula, and your working distance is like 20 centimeters, working distance would equal +5 in this formula. But that's confusing because we end up like adding -5 to the phoropter. So if you think about it this way, we can do gross plus working distance as a minus number. So in this case, it would be gross plus whatever our working distance is equals net. And our net, we know, is -5 because of this. So -5. So at what distance would you see 1 diopter of against motion? So we know our net is -5. And our gross, so our gross is what's in the phoropter before we take our working distance out, right? So our gross has to be -1 because we figured that out from the problem. And then all we have left is the working distance. So if we solve for WD, we do +1, +1, and then working distance equals -4. So at what distance do we get -4? We do the punctum remotum, so 100 over -4. It doesn't matter about the sign. We get 25 centimeters. Okay, so that's our answer. So we have 25 centimeters. Okay, and then at what distance would you see 1 diopter of with motion? So we know with motion means it's +1. So then we go back to my backwards version of the formula, which is gross plus working distance equals net. So our gross is +1, which we figured out from what the question says. We don't know our working distance, and our gross is still -5. So now, if we solve for working distance, we do -1, and then we get working distance equals -6. And so then we do 100 divided by 6, which I don't know, so I have to solve. You get 16.67 centimeters. So our answer is 16.67 centimeters. Okay, and then what gross lens would you see neutral at 67 centimeters? Okay, so in this case, I'm going to keep using my backwards version of the formula. So again, we have gross plus working distance equals net, and we know our net is -5, and our working distance is 67 centimeters, and that correlates to, so I'm doing 100 divided by 67, and so our working distance is -1.50, and then we have our gross. Okay, I'm just gonna remind you, if you do my formula this way, the working distance number is always minus. If you do the formula the way Dr. Kaiser taught, the working distance is always plus. I just prefer it my way. So if we do this, gross equals plus 6.850. I'm sorry, I did that wrong. It's minus 3.5. Okay, so yeah, that's how you solve these. I just want to remind you that the way Dr. Kaiser taught is that, I'm just going to erase this. The way Dr. Kaiser taught was this formula right here, the top one. And in that formula, the working distance is always plus. In my version, which is the same formula but just switched around, the working distance is just a minus number. And that helps me organize it a little bit better. To be honest, I don't actually really use the formula. I kind of just see it as at what distance. Let's say we're looking at letter B. We know the refractive error is -5, so that's where we have to end up after we take our working distance out. So at what distance would you see 1 diopter of against motion? So what that's telling us is that we start with neutral, and we see against motion, and we neutralize it once we reach -1. So our 4-opter will read -1. We have to end up at -5. The difference is -4. And then 100 divided by 4 equals 25 centimeters. So it's just a shortcut. Don't confuse yourself if that seems too complicated or difficult. Just do the formula for now. But I encourage you to consider using the formula my way, even if it's somehow wrong, and I hope Dr. Kaiser doesn't get mad at me, but it makes more sense to make the working distance a minus number and to put it on the same side as the gross. Okay, so with all that being said, let's move on to number 2, which should go by faster. Okay, so we have a schematic eye. We place a -5 sphere in front of the eye, so that means the refractive error is +5. If that's the case, it's a plus number. What distance would you see neutral? It's impossible. Because there's no distance where you could be where after you're done, you take out your working distance and you add plus. That just doesn't happen. So at what motion would you see at 100 centimeters? So no matter what, I think since the patient's the schematic eye's prescription is +5, no matter what happens when you start any plus refractive error, whenever you start retinoscopy, you're going to see width motion. So I already know the answers to these are width and width, but I'll make the question a little bit more difficult and say, how much width motion would you see at 100 centimeters? So if we correlate 100 centimeters to like a working distance, we know 100 over 100 equals 1. So what that means is this is our working distance. Our gross is what we're solving for. Minus 1, because that's our working distance, equals our net, which is plus 5. So then if we solve for that, we get gross equals plus 6. So what that means is we'd get into the phoropter, we'd see width motion, we'd neutralize that by adding plus lenses until we reach plus 6, and then we take our working distance of 1 diopter out, and we'd end up with plus 5. So let's do the same thing for C. At what distance? What motion would you see at 50 centimeters? We know it's width, so if we do 100 divided by 50, that equals 2. So that's our working distance. Our gross minus 2 equals our net, which is plus 5, and so our gross would be plus 7. So I'll walk that through again. We would start retinoscopy with the phoropter at 0. We would see width motion. We'd add plus lenses until we end up at plus 7. Gross is always what is in the phoropter before you take your working distance out. So we see plus 7, we're done, and then we take out our working distance of 2 diopters, and we end up with plus 5, which is correct. What gross lenses would give you neutral at 67 centimeters? So we know 100 divided by 67 centimeters is 1.5. So that's our working distance. Our gross is what we're solving for. And our working distance is 150, so I'm going to do minus 150 equals plus 5. And then, so if we solve for gross, that's plus 650. Okay, and then we'll move on to number 3. So we have a schematic eye. We're working at 50 centimeters. And we place minus 75, minus 125, axis 90 in front of the schematic eye. So before we even tackle any of the issues, let's figure out what the refractive error of the schematic eye is. So when it comes to the ones with astigmatism, I want you to write out your optical cross. So we have optical cross here. Axis 90 is over here, and then axis 180 is over here. So on axis 90, we know the first number correlates with the axis. So the first number is minus 75, and that's at axis 90. And then the SIL is minus 125, so that's the difference between this meridian and this meridian. So minus 75, and we add minus 125 to that, so the other meridian is minus 2, and that's axis 180. Okay, so this is the prescription we put in front of the eye. But that's not the refractive error. Remember, it's the exact opposite. So for the refractive error, it's the exact opposite. We draw the same optical cross, but we just switch the signs of the prescription. So now it's plus 75 right here and plus 2 here. Okay, now I want you to be very careful with this, because once you flip the signs, your axis is going to change. The reason for that is our axis is always named after the least plus or the most, the least minus or the most plus meridian. So in our original one over here, our least minus or most plus meridian was this minus 75, because minus 75 is less minus than minus 2. Or it's more positive than minus 2. In this flip scenario, plus 75 is more minus than plus 2. So, or plus 2 is more positive than plus 75. So, because of that, plus 75 is still at axis 90, plus 2 is still at axis 180, but our final RX is going to be like named by the meridian with a higher plus value. So in this case, our new axis is going to be 180. So the prescription of our, like the refractive error of our schematic eye is actually going to be +2 because that's the most plus meridian. Axis 180 because that's the axis of our most plus meridian. And then the sill is just going to be the difference between these two numbers. This fortunately does not change, so it's still going to be -125. And you can check that because the difference between +2 and +75 is -125. Okay, so now we know the refractive error of the schematic eye. I'm just going to delete all of this. Okay. What motion would you see with your streak oriented at 90 degrees? Now, I need you guys to pay a lot of attention to the wording that they use on the exam, because it says oriented at 90 degrees, but that is not the meridian you're scoping, okay? If it ever says oriented or parallel to like a certain meridian, you are scoping the opposite. So what it's actually saying is, what motion would you see when you are scoping axis 180? Okay? So I'll just redraw the optical cross. So +2 here, +75 here. Okay, so what motion would you see when your streak is oriented at 90 degrees, aka you're scoping the 180 degree axis? So if you're scoping the 180 degree axis, you're scoping to see this +2, okay? Since it's plus, we're gonna see with motion. Okay, what motion would you see when your streak is oriented at 180 degrees? So that means it's oriented at or parallel to 180, which means we are scoping 90. If we're scoping 90, we're scoping this +75, which is still plus, so we're going to see with motion. Okay, what would the net lens correction be? So that's just saying what is the refractive error of the schematic eye. We already decided that. That is +2 -1.25 axis 180. Okay, what would the gross lens to get neutral at 50 centimeters be? Okay, to solve these, you can just do the same thing that I showed you earlier, which is gross plus working distance equals net. Okay, the thing you have to remember with this is that you don't really need to mess with the sill. When it comes to like gross lenses overall, we are talking about just like the sphere technically. So our net can just be +2. Our working distance is since at 50 centimeters is -2, and then our gross is here. So if we do this, we solve for gross equals +4, and then we just add the rest of the prescription. So it's +4 -1.25 axis 1. Okay, so then I'll do number 4. I'm going to move a little bit faster this time. So we place a +325 -125 axis 180 in front of the schematic eye. So I'm just going to draw that out. So here's my optical cross. +325 is along the 180th. And then 90 degrees away from that, at axis 90 is the sill, so the difference is -125, so +325 -125, that's +2. Okay, now we're going to flip it. So now it's going to become -2 on this side, and then -3.25. And so our new, and then remember, this is axis 90, and this is axis 180. So the axes stayed the same, but because now -2 is the more positive axis, the new axis is going to be 90. -2 is going to be the sphere, and then -1.25 is going to be the sill. I'm just going to clear some space. So it was -2, -1.25, axis 90, and then just to keep track, minus 2 is at 90, and minus 3.25 is at 180. Okay, what motion would you see when the streak is oriented at 90 degrees, which means we are scoping the 180th? Okay, so if we're scoping the 180th, we're scoping minus 325. Okay, so we're scoping minus 325. Our working distance is 50 centimeters. Okay, so let's use the formula so we can be sure. So it's saying what's our gross. It's not asking what our gross is, but that'll help us get to our final answer. So gross, and our working distance is 50 centimeters, which is 2 diopters. So we can do gross minus 2 equals, and our net in this case will be whatever amount we're scoping. So we're scoping minus 325. So that's our net, minus 3.25. And so then our gross is minus 1.25. Okay, so if you use the formula to solve for a number when you have a problem like this, all you need to see whether it's minus, plus, or neutral. Okay, if it's minus, you get against motion. If it's plus, it's with motion, and if it's neutral, you see neutral. Okay, so since we see a minus number, we know this is against. Okay, the minus 1.25 would be the answer if the question was how much blank motion would you see when the streak is oriented at 90 degrees. You would see minus 1.25 of diopters of against motion. Okay, now let's move on to part B. What motion would you see when your streak is oriented at 180 degrees? Okay, I'm now realizing I did that whole problem backwards, so actually no, I didn't, sorry. I'll keep going. So what motion would you see when your streak is oriented at 180 degrees? If it's oriented at 180 degrees, we're scoping 90, so we're scoping minus 2. Okay, and now is how, like, one of those scenarios where this can be tricky. Okay, so logically thinking, okay, we're scoping a meridian where there's a minus number, so we're probably going to see against motion. Okay, sure. But if you do the formula, which is gross minus 2, because our working distance is 50 centimeters, equals minus 2, and you solve for gross, you will get 0. So after doing that, you realize that the answer is actually, you would see neutral or no motion. Okay. So I'll erase that. So that's the answer for this for part B, is that you'd see no motion. What would be the net lens correction is just what we solved for earlier, which is minus 2, minus 1.25, axis 90. And then what would the gross lens to get neutral at 50 centimeters be? Okay, so then again, when you have one of these, let's just take the sphere, and that's our net. Our gross is here, and then our working distance is minus 2, and then so we solve for gross, and that equals 0. So then our final answer would be PL, which is 0, minus 1.25. So we're just keeping the axis in the sill, minus 1.25, axis 90.